Right. We have already made some basic concepts about the electrical activity of the heart. Now we will discuss first that what are the electrical events in the heart during one cardiac cycle. What is our discussion? First of all, we will discuss about the electrical events in the heart. Electrical events in heart during, yes please, during one cardiac cycle, right? And then we will see that how these electrical events in the heart translate into vectors. Is that right? How the different electrical events in the heart during one cardiac cycle translate or they lead to formation of cardiac vectors. That is cardiac vectors. And then we will see that how these cardiac vectors which are produced, these electrical vectors which are produced during one cardiac cycle, how they are translated into, yes please, ECG pattern, different waves and intervals, right? So again, we are going to discuss, further discussion is in three phases. Number one, what are the electrical events in the heart and different electrical events during one cardiac cycle, what type of electrical vectors and cardiac vectors are produced, and eventually how those cardiac vectors are translated into ECG pattern. Let's suppose here is your heart, right? I draw a big heart here, and of course this is your which chambers? Atrial chambers. And what are here? Ventricular chambers, right? Now, you know, electrical activity in the heart start with the depolarization of SA node. In a normal heart, we are going to talk about the electrical activity of normal heart, right? Previously we discussed only electrical activity in few cells. Now we are talking about whole heart generating electrical patterns. So at the beginning of the cardiac cycle, SA node fires, and when SA node fires, it generates the wave of depolarization. The wave of depolarization which is produced by SA node, right? Let me make a simple heart here. That wave of depolarization which is generated by SA node, first of all, it stimulates the cells which are near the SA node. The cells which are adjacent to the SA node, let's suppose these are the cells, first of all, they are stimulated and these cells undergo depolarization. First group of cell. And as you know, these cells will be connected with the next group of cells that will lead to depolarization of the second group of cells. And of course, then depolarization will move from the second group of the cells to the third group of cells. So as soon as SA node fires, wave of depolarization is produced, right? And this wave of depolarization, which is first produced near the SA node, right? This wave of depolarization start moving to the next group of cells. Eventually what happens, we see that electrical current or wave of depolarization is sweeping from SA node to within the atrial myocardium, right, downward and leftward, right? It means atria are being depolarized downward and leftward. Why atria are depolarized downward and leftward? Because origin of depolarization, that is SA node, is present in the atria on the right side and upper side. Because in both atria which are stimulated by the SA node, but position of the SA node is right and up. So from here you can say electrical current is generated in this fashion, right? And these small vectors which are generated due to waves of depolarization, these vectors are moving downward and leftward. And again you remember the right atrium and left atrium, they are syncytium. Is that right? Due to that reason, electrical current sweeps simultaneously on the right atrium and left atrium. Right? Now all these vectors, depolarizing currents, can be added together. Right? And when they are added together, then what really happens that all of them together, they will make one single vector which is directed downward and leftward. Now, this vector is representing the electromagnetic force which is produced in the heart when both atria are undergoing the process of depolarization. Both atria are having the spread of depolarization. So this is atrial depolarization vector. Right? Now, atria are thin. Atrial myocardium is thin. Because atrial myocardium is thin, so this vector will be small. Secondly, atria do not have very specialized and very fast conducting system. Atria undergo depolarization moderately. So we say there is a small vector which is moving downward and leftward. Is that right? And with moderate velocity. This is the first electrical event in the heart during the cardiac cycle. What is the first electrical event? Atrial depolarization. Is that right? And that is represented by, atrial depolarization is represented by a vector which is small vector, moving, small depolarizing vector moving downward and leftward with moderate velocity. Am I clear? This is the first electrical event. So in a simple diagram, we can represent the first electrical event like this. Right? So this is your first electrical event. Clear? After that, when both atria are completely depolarized, right? When both atria are completely depolarized, then what happens? That these depolarizing waves will hit the fibrous annulus. Now, this fibrous tissue which is present between the atria and ventricle, this is not a very good conductor. So most of the depolarizing current which hit this fibrous partition, right, that will die out, because from here, from these points, depolarization cannot go down. The only single point from where depolarization can go from atria down to the ventricle is AV node. What is that point? Yes, please. AV node. The only electrical window between the atria and ventricle is AV node. So all the electrical depolarizing currents which hit to the fibrous septum, they will be dead. The only those electrical depolarizations which hit the AV node, they will be taking the current gradually to the ventricle. Is that right? So first electrical event is depolarization of atria, which is represented by a small vector moving downward and leftward, right? Small depolarizing vector moving downward and leftward with moderate velocity. The second electrical event is that stimulation of AV node. What is the second electrical event? That is stimulation of AV node. Now, let me draw the AV node as a large tissue. Let's suppose this is the AV node. Now, AV node has a very specialization. AV node is modified myocardium. It is a specialized myocardium, and AV node is specialized in slow conduction. AV node is specialized in slow conduction because when atrial current touches the AV node conducts the current very, very slowly, so that current takes, or depolarization take, about 0.1 second just to reach from atrium to the ventricle. Why current is slowed down at the junction of atria and ventricle at the point of AV node? Why current is slowed down? Why velocity of depolarization becomes slow? There's a reason for that. Because now atria are contracting. If current is held in AV node or stopped in AV node for a while, that is good, so that atria complete their contraction and fill the ventricles. Only when atria has completed their contraction, then electrically ventricles should be stimulated so that ventricles start contracting. Is that right? First atria should contract, after that ventricles should contract. Due to that reason, when atria are electrically stimulated, right, current is passed through the AV node very, very slowly down to the ventricle. Is that right? So AV node is specialized in slow conduction. AV node is specialized in slow conduction. Now, how AV node is specialized in slow conduction? There are many reasons. Number one, let's suppose we talk about two tissues in the heart. Number one, AV node, which is specialized in slow conduction, and later on I will explain this is Purkinje system. And this Purkinje system, right bundle branch and left bundle branch and its Purkinje fibers, this is also a specialized myocardial cells, and this tissue is specialized in fast conduction. Again, AV node is specialized in slow conduction, and bundle branches and their Purkinje fibers are specialized in fast conduction. Why this is specialized in slow conduction? So that current from it, while it is jumping from atria to the ventricle, it should be held here for a while until atria complete their contraction. And why after that, when current from AV node is released into ventricle, why in the ventricle there is a very fast conducting tissue? Because all the ventricle should get electrical stimulation at almost simultaneous time, so that septum of the ventricle, major part of the ventricle and basal part of the ventricle, all of them contract at almost simultaneous time, so that there should be effective ventricular output. Is that right? Now, why AV node is slow conductor and why Purkinje system is fast conduction? Let me tell you. Let's suppose AV node is 0.1 to 0.2 and Purkinje fibers are, this is Purkinje tissue, it has cells and these are Purkinje cells. These three cells I show, these are for example from 0.3 to 0.4, right? Now, this tissue is slow conductor, right? And this is Purkinje system, which is, yes please, fast conductor. Why AV node is slow? Because number one, AV node has very, very small cells, and these cells are arranged in such a way that cells are not, you can say, listen again, these are AV nodal cells. AV node has a lot of cells, but these are very small cells, and these cells are arranged right angle to the direction of current flow. This is Purkinje system. Current has to move in this direction. Let's suppose depolarization has to move in this direction and in this direction. Now, in AV nodal, there are many cells and small cells. In Purkinje system, there are large cells and less cells. So, because point A to point 2, right, there are more cells involved, so more membranes to be crossed, so it is slow conduction. Here there are large cells and there are less cells involved, so less membranes involved in electrical event, so conduction will be fast. This is one reason. Second reason is the number of gap junctions between the AV nodal cells are very, very less, but number of gap junctions between Purkinje cells are too much. So we can say that electrical windows between the AV nodal cells are very few, but electrical windows between the Purkinje cells are too many. So naturally, current will conduct from one cell to the next cell slowly in AV nodal system, but current will conduct from one cell to the next cell very fastly in Purkinje system. Is that right? Then another thing. AV node depolarization is dependent on calcium, and depolarization in Purkinje system is dependent on sodium. Calcium channel works slowly, sodium channels work fastly. So in AV node, yes, current movement is slow, and in case of Purkinje system, current movement is fast. Then the most and another important point, AV nodal cells are less diameter cells, right? So they offer more resistance to the current movement. But Purkinje cells are wide diameter, because they are very wide diameter. So even within the cell, the current has less resistance to the movement. So current moves fastly. And now we will come to the most important point. What is the most important point? That this is slow conductor and that is fast conductor is that AV nodal cell resting membrane potential is minus 60 millivolt. But Purkinje system cell has a resting membrane potential of minus 90 millivolt. So which cell is more electronegative? AV nodal cell or Purkinje cell? Purkinje cell is more electronegative. Now, if cations have to move into AV nodal cell as well as cations have to move in Purkinje cells, where the cations will move very rapidly in the cell which is more electronegative, because this is the electronegativity of the cell which attract the cations during depolarization. So depolarizing current in AV node are slow and depolarizing current in Purkinje systems are fast. So due to all these factors combined together, AV node is specialized in very slow conduction and Purkinje system is specialized in very fast conduction. So once you have understood this, now we come back to the next electrical event, right? First electrical event was, yes please, what was first electrical event? That was atrial depolarization. And let me draw a heart here. Okay, let me draw a smaller heart. Yeah. Right? This is the fibrous septum between the or annulus. Now, what is here? This is left ventricle and this is right ventricle, right? And here is your friend SA node. Is that right? The first electrical event was that SA node produced the depolarization and there were atrial depolarization, and atrial depolarization was represented by a small vector, depolarizing vector moving downward and leftward with modest velocity. Now the second important event is, yes, current passing through AV node. This is the second electrical event. I told you that AV node is a fast conductor or slow conductor. It is extremely slow conductor. This is point number one. And point number two, as compared to the rest of the heart, AV node is a large tissue or small tissue? Small tissue. AV node is a very tiny myocardial tissue, very small tissue. So when current is moving through the AV node, do you think AV nodal depolarization will produce a very big vector or very small vector? It will make a very small vector, right? Because AV node is a very tiny myocardial tissue. So when depolarizing current is passing through the AV node, number one, that current is passing through very slowly, and number two, that AV node is a very tiny tissue, very small tissue. So electrical vector is very small when AV node is undergoing depolarization process. And because the electrical vector is very small, that ECG machine will not pick that up. When ECG machine does not pick the electrical activity of AV node, right? So actually for practical purposes, when a very miniature depolarization is passing through AV node, heart is electrically silent. You get it? You say that AV node just whispers, it does not talk. And our machine cannot hear AV nodal electrical activity. So we can say for practical purposes, I put a question mark. That electrical activity is there, but it is so small electrical activity that our machines cannot pick up, right? So we can say that there is electrical silence in the heart. When AV node is passing through depolarization process, when AV node conduction is going on, we say heart is electrically silent. Heart is electrically silent. Is that right? So for about 0.1 second, or the duration for which current is passing through AV node, heart become electrically silent and no significant electrical vector is produced to fluctuate the needle. Is that right? Now we come to the next cardiac event. Next electrical event in the cardiac cycle is that now current has come to yes please, where it has reached? To Purkinje system. Through bundle of hairs, current will come to the right bundle branch and it will go to the, yes please, left bundle branch. And these bundle branches are made of specialized myocardial cells which are called Purkinje cells. And Purkinje cells are specialized in slow conduction or fast conduction. These are specialized in fast conduction. Is that right? Now, listen carefully. That the current, electrical current, as soon as it is released by AV node into Purkinje system, first they will depolarize the septum of the ventricle. Then the current will go to the major portions of the ventricles. And this is the apex of the ventricle and this is the base of the ventricle. As current is, yes, current means depolarizing current. As depolarizing current enters into ventricles through the bundle of hairs and bundle branches, the first portion to be depolarized are septum of the ventricle, interventricular septum. The next portion which will be depolarized is major part of the ventricle, and last portion of the ventricle which receives the current, because current is moving like this and like this. This is the base of the ventricle. Remember, this is the apex, this is the base of the ventricle. So it means that ventricle depolarizes in 3 stages. First, there is the very rapid stage of septal depolarization, then major ventricular depolarization and basal depolarization. I will analyze the depolarization of every stage one by one and make their vectorial analysis. Let's make another separate diagram to understand. Okay, let's suppose this is the interventricular septum and this is the left ventricle and here it is right ventricle. This is the right ventricular myocardium, right? This is the left ventricular myocardium, and let's suppose that here it is your friend AV node. Naturally, when current was passing through AV node, heart was electrically silent. Then current was released through bundle of hairs to, yes, it is released where? To the bundle branches. And these bundle branches will take the current to the septum, right? Now first I will show you how the ventricular septum undergoes depolarization. Now this is the septal myocardium. Remember, the interventricular septum, upper part is fibrous. Upper part is, yes please, fibrous, and lower part is muscular. This is fibrous tissue and lower part is muscular. Now actually fibrous tissue make a sleeve around these bundle branches, and this fibrous covering on the bundle branches are acting as insulating layer. As wires have the rubber sleeving, electrical wires have a rubber on them, rubber act as insulator. In the same way, when bundle branches are coming down, they are having fibrous cover on that, right, act as insulator. Now, this is the ventricular septal myocardium. This is septal myocardium. Septal myocardium is stimulated by the left bundle branch. It is not stimulated by the right bundle branch. Why? Because there are some connections here, and left bundle branch gives stimulation to the septal myocardium. But right bundle branch take the current downward, but it does not stimulate directly to septum. So it means myocardial septum is stimulated by the left side or by the right side? It is left side. So first there will be depolarization of left side of the interventricular septum. And this wave of depolarization will start from the left side of the septum, right? It is not only left side of the septum which stimulate, it is also stimulate the lower part of the septum. So we say wave of depolarization is produced in the ventricular septum in its lower and left portion. And this wave of depolarization sweeps from the left side, right side, and from lower to upper part. So this wave of depolarization moves from left to right and from down to up. So we can say that when ventricular septum is undergoing depolarization process, right, depolarizing currents are moving from left and lower portion of the septum towards right and upper portion. Is that right? Now, so we can make a vector of it. The vector of this septal depolarizing current, the depolarizing vector is a small vector. Why? Because as compared to the big part of the ventricle, septum is having little myocardium. Is that right? So there is a small vector, but this vector is moving, yes, rightward and upward. Right? So this vector represents electrical activity of septal depolarization. Now you understand why the septal depolarization is a small vector, because myocardial septum is a small tissue. Number one, it's small vector. Number two, this vector is directed rightward and upward because left bundle branch stimulate the left and lower portion of the myocardium. From there, current moves to rightward and upward. Right? So we can show in this diagram this vector. Right? And this vector is a small vector. Right? This is a small vector, depolarizing vector, and this vector represents which activity? Septal depolarization, which is rightward and upward. Do you think it's a moderate or slow conductor or fast conductor? Of course, it has Purkinje's system, and that helps it fast conduction. So we can say during the septal depolarization, ventricular septal depolarization, electrical vector is generated, which is small but fast vector, which is moving rightward and upward. Right? So how many electrical events we have discussed? Number one, atrial depolarization. When SA node fired, there was atrial depolarization, a small vector moving downward and leftward with moderate velocity, not fast velocity. Next electrical event was current was passing through AV node. But when current was passing through AV node, right, conduction was very slow and AV nodal tissue is extremely small, so electrical activity is not significant enough to move the ECG machine needle. So we say during the AV nodal conduction, heart is electrically silent. These are the first two events. Next event is onset of depolarization of ventricle. The first portion of the ventricle which undergoes depolarization is septum of ventricle. Septum of ventricle is depolarization produces a small vector moving rightward and upward, but it is not a slow vector, it is a very fast vector. Is that right? After that, now current will reach to the, it has passed through this area, it has stimulated the septum. Now there are branches coming out of Purkinje's system. Is that right? There is right bundle branch and there is left bundle branch. Right? Now wave of depolarization comes from these bundle branches and their Purkinje fibers to the ventricular myocardium. Let's suppose I show you that these are Purkinje cells. These two are Purkinje cells. And they are connected with, what are these? Myocardial cells. So naturally, first cell will stimulate the second in a fast way, and then that will conduct current to the third, then depolarization will go to the fourth cell and fifth cell. A very important point to be noted. What is a very important point to be noted? That Purkinje fibers are in the deeper myocardium. Right? Myocardium has two parts. This myocardium, let's suppose this is myocardium, innermost part, inner myocardium, this is the middle myocardium and this is outer myocardium in the ventricles. This is called subendocardial myocardium because this myocardium is just under the endocardium and this myocardium is just under the pericardium. So some people call inner myocardium as subendocardial myocardium and outer myocardium as subpericardial myocardium, because here is your endocardium and here it is your pericardium. Is that clear? Now, the point which should be noted is that this Purkinje system, it is not in the middle of this. It is into very deep myocardium or inner myocardium. So which part of the myocardium will be first depolarized? That is the inner myocardium. Is that right? So depolarizing currents are generated in the major part of the ventricle, first in the inner myocardium. Is that right? So inner myocardium is first stimulated and then depolarization moves outward. Again, because specialized conduction system is embedded in deepest most myocardium, or this specialized conduction system is very near to the deepest myocardium or inner myocardium. So inner myocardium is first stimulated and then wave of depolarization moves outward. What does it mean? It means that first of all, these tissues are depolarized. Is that right? These are first depolarized. And then after that, wave of depolarization moves like this. What do you really see? That wave of depolarization is moving from inner myocardium to outer myocardium. Is that right? Now, another point which you have to note it, that left ventricle is 3 times thicker than the right ventricle. So naturally, depolarizing currents are produced in the left ventricle strongly, and as compared to the left ventricle, depolarizing currents and vectors are produced in the right ventricle relatively weak. Am I clear? Because left ventricle is thick. So depolarizing vector, let's suppose this is depolarizing vector. This is directed like this. It is stronger vector. But here, because it is thin, so vector is smaller. And there is not one vector. Many vectors are produced. Is that right? These vectors represent depolarization of right ventricle, and these are representing depolarization of, yes, left ventricle. Is that right? Now, all these vectors are produced almost simultaneously. And you know, when multiple vectors are produced simultaneously, they can be added together. So, when left ventricle is undergoing depolarization, right, we can make a single vector. This vector represents left ventricular depolarization. Is that right? And this vector represents right ventricular depolarization. You can see left ventricular vector is stronger and right ventricular depolarization vector is weaker. Is that right? Again, let me repeat it. Ventricle is depolarized in 3 stages. First of all, septum is depolarized, then left and right major ventricular portions are depolarized from in to out, and lastly we'll discuss basal areas are depolarized. When left ventricle is depolarized, a vector is produced like this, and when right ventricle is depolarized, vector is produced like that. Now, left ventricular major depolarization vector is downward and leftward. Right ventricular depolarization is downward and rightward. But left ventricular vector is stronger and right ventricular vector is weaker, because both of them are same time, right? They are generated at the same times, so they can be added together. And if we add them together, this is the vector which represent the depolarization of, yes, this vector represents the depolarization of major part of both ventricles. Is that right? Again, this vector is left ventricular depolarization vector, this is right ventricular depolarization vector, but because they are in the same time, so they can be added together. But because left ventricular vector is stronger and right ventricular vector is weaker, so net vector is directed downward and leftward. So this is the net vector representing the major ventricular depolarization, major left and right ventricular depolarization. Am I clear? And once septum is depolarized and major part of ventricles are depolarized, then eventually depolarization wave will reach to the basal area. These are the basal part of ventricles. So they will be the last to be depolarized, and here depolarizing current is moving from, okay, let me make the diagram more clear. Now, here the current will be moving from down to up and rightward. Here also it is moving upward and rightward. So there will be small vectors made by the depolarization process in the basal part of the ventricles. But these vectors are moving upward and rightward. Why it is so? Because again, why it is so? The reason being that this is moving upward and rightward, this is also moving upward and rightward. These two vectors represent ventricular basal depolarization. Base of the ventricle undergoing depolarization. This is the last depolarizing event in ventricular depolarization. These are small vectors moving upward and rightward. But remember, all these electrical vectors which are produced in the ventricle, these are fast vector because ventricles have special fast conduction system which is called Purkinje system. Am I clear? Any question up to this? So, what have we learned? That during one cardiac cycle up to now, how many vectors are generated one by one? How many electrical events are generated one by one? Right? Okay, let me make this diagram again, but without much revision. Let's suppose I draw your heart here. These are left and right. Remember again, atrial myocardial tissue and ventricular myocardial tissue is separated by the fibrous septum. This is the fibrous septum, and the only one point through which the current can move from atria to the ventricle is through, in a healthy heart, current can move through, yes, AV node. Is that right? And of course here is specialized Purkinje system. Again, now we put all the electrical events in perspective. First event was atrial depolarization, having a small vector moving downward and leftward with moderate velocity. This was first electrical event. Second electrical event was AV nodal silence. Third electrical event was, what was this? Septal. Now ventricular depolarization start. There are three vectors for ventricular depolarization. First, septal ventricular depolarization, then major ventricular depolarization, then basal ventricular depolarization. Septal ventricular depolarization make a small vector but moving rightward and upward, but fast vector. And what is this vector? This is vector representing major ventricular depolarization. Am I clear? And in the end, these small vectors represent what? Yes, basal ventricular depolarization. Am I clear? So these are the, now atrial depolarization is done by this vector. When then AV node is showing the silence, then ventricular depolarization process start. When ventricular depolarization process start, at that very time, atria is undergoing repolarization. So repolarizing current in the atria is masked by the depolarizing activity in the ventricles, right? Now, let's suppose we go to the next stage. First electrical activity, second, third, fourth, and here is the fifth. Now, let's take these electrical graphs, electrical vectors, right, of this heart and apply a galvanometer there. You remember the galvanometer from last lecture? Let's see it. Here is this man. He's very happy. You know why he's happy? Because he understands the ECG to some extent now. So he's very, very happy. Okay. Right? I've shown a very big heart there, but actually heart is of course smaller. But what I'm showing, that this is the heart of this person. These are the electrical events in his heart during one cardiac cycle. I have not shown the ventricular repolarization. That I will discuss later, right? Now, what we do, we apply our galvanometer to this person and see what are the needle fluctuation due to these vectors. It will be fun. Now, let's suppose that here is our galvanometer, and we break down its window and take its needle out. This is that galvanometer. Here it has, we apply, let's suppose, positive electrode on the foot, left foot. Suppose we apply the positive electrode here, and we apply the negative electrode. What is this? Right arm. So the same galvanometer we have applied to this person, and we want to see what type of needle fluctuations are produced by the electrical activity of the heart. Because when during one cardiac cycle, electrical vectors are produced due to electrical events, and these electrical vectors and electrical potentials are very faithfully conducted to the body surface through the body fluids. The very small electrical activity of the heart produces very miniature voltages up to skin. Body is a very good volume conductor, right? Even very small electrical currents which are produced during the one cardiac cycle or each cardiac cycle, they are very faithfully conducted up to the body surface. It is such a volume, good conductor. If you don't trust that body is a good conductor, you can do a small experiment. Put your finger into any electrical plug. Suddenly you will know that body is a very good conductor. Take care, don't do it anywhere. Alright? Now listen. So electrical activity of heart come to the body surface. So we can apply the electrode on the body surface and pick up the electrical activity which is going on deep into heart. Is that right? Now listen. We have applied the positive electrode on the foot because it is convenient to apply here. But actually, whatever electrical current is coming to this point, this will be conducted to the foot. So it means applying the electrode to the foot is equivalent to applying the electrode at the junction of the left lower limb and the trunk. In the same way, when you apply the electrode on the right arm, actually position of electrode, that position of the electrode will sense the same electrical activity which electrode could sense when electrode is applied at the junction of right upper limb and the trunk. Right? Again, let me repeat it. For key convenience, I have applied the negative electrode here and positive electrode on the foot. Is that right? Basically, whatever electrical activity is here is the same which is conducted in the arm. So either you put electrode here or here, it will be receiving the same result. In the same way, you apply the electrode here or you apply the electrode on the foot, right? What really happens, that electrical activity which is reaching here, right, that will be recorded. Is that right? Now, so for practical purposes, we can say that positive electrode which is on the foot is actually here, right? This is the positive electrode, and negative electrode which is on the right arm, right? This is practically here, right? Now these are the positions of the electrodes, and we have to see that how these vectors will move this needle. Let's do a little scientific work. What we do, we take a paper roll of paper, and this is a roll of paper. Is that right? This is paper roll. We put it vertically, and here let's suppose This is a wooden stand, and we have applied this paper roll on the stand. Is that right? We are making ECG machine by one moving paper roll and a galvanometer. That's the simplest form of ECG machine. Here is a small motor, and this motor is constantly moving the paper in this direction, right? So paper is moving in this way. Is that right? Paper is moving in this direction. Now what we do? We are ready with our ECG machine. This was galvanometer, very sensitive one. Put positive electrode here, negative electrode on the right side of the trunk, right upper side. Clear? More truly speaking, on the right arm. Now, we brought this needle out, and let's suppose on this needle tip we put some black ink. We put a black ink. Is that right? And we make the switch on, and this paper start moving under the needle. When this paper is moving under the needle, if there is no electrical activity in the heart, listen now carefully, rather you have to answer. If there is no electrical activity in the heart, right, no vectors are there, do you think this needle will fluctuate or it will remain at a steady point, neutral position? So when there is no electrical activity in the heart, these electrons don't sense anything, needle will remain at the neutral position. Because paper is moving under the needle, so it will make a straight line. Is that right? Then suddenly SA node fires. And first electrical event start. That is the spreading of depolarization on atria. And which electrical vector is produced? Atrial vector is produced. What is produced? Atrial vector is produced. When this atrial vector is produced, this atrial depolarizing vector is moving towards the positive electrode or away? It is moving towards the positive electrode. So deflection should be positive. You know that when positive charges move to the positive electrode, deflection will be positive. So needle will move upward. Remember that this is zero position. Here it is positive side and this is negative side. Deflections which are upward, they are positive deflection. Deflections which are downward, they are negative deflection. So when atria is undergoing depolarization, a small vector is moving towards the positive electrode, so there will be small positive deflection. And it is moderate velocity. So this will be, needle will go upward positively with moderate speed, not fast speed. So as paper is moving under it, so during atrial depolarization, when needle is gradually lifted upward, as this vector is moving towards the positive electrode, this wave will be generated on the paper. This wave represent what thing? Atrial depolarization. This wave is generated by the needle in response to atrial depolarizing vector, right? And this is a slow wave, not a fast wave. Is that right? And a small deflection because atrial vector is small one. What is the next electrical event? Now atria are completely depolarized. When atria are completely depolarized, needle will come back to neutral position. Clear? Now the next electrical event is, what is this? AV nodal depolarization. When AV node is undergoing depolarization, do you think there is any significant current which will move the needle? No. So we say this electrically, heart is silent. We say this AV nodal silence. So when current is conducting through AV node, these electrodes don't pick up any activity, so needle will remain straight. So after the end of the atrial depolarization and before the beginning of ventricular depolarization, current is held in AV node, but that current activity is so small that needle is not, electrode don't sense anything, needle will not move, so there will be a straight line. So this straight line represents that needle is not fluctuating. Why the needle is not fluctuating? Because right now current is passing through AV node, and AV node is a small tissue. Electrical activity is so small the needle does not fluctuate. Is that right? So this small piece, right, this represent conduction through AV node. Is that right? What is the next electrical event? suddenly current is released into Purkinje system. As soon as current is released into Purkinje system, ventricular depolarization start. Depolarization wave spreads through the ventricle. The first electrical event is septal depolarization. Now, when ventricular septal is undergoing depolarization, a small vector is produced. So there will be small deflection. But this vector is moving towards the positive electrode, or this vector is moving away? Because this vector is moving away from the positive electrode, so deflection will be negative, but small deflection. And because it is fast vector, so there is small deflection which is negative but slow or fast? Fast. So needle will move when ventricular depolarization is there. Needle will move fastly, a little deflection down and then come back. So when it will rapidly move, it will make a wave like this. So this wave, this needle fluctuation represent ventricular septal depolarization. Is that right? The first wave is called P wave. So P wave represent atrial depolarization. After that, this straight line represent conduction through AV node. Then this is showing the onset of ventricular depolarization. And this small but fast negative wave, here it is representing what? Ventricular septal depolarization. Right? Now, what is the next electrical event? Next electrical event is current is going now to the major part of the both ventricles. And both ventricles, when major ventricular depolarization is start going on, now the next electrical event is after the septal depolarization, there is major ventricular depolarization. During major ventricular depolarization, a very strong vector is produced downward and leftward, strong and fast. The strong and fast vector, which is representing the electrical activity in major ventricular depolarization, this vector is moving towards the positive electrode or away? It is moving towards the positive electrode. So deflection will be negative or positive? It will be positive because positive charge is moving towards the positive electrode. So deflection will be positive, number one. Number two, deflection will be slow or fast? Fast. And deflection will be small or big? So what happens? Strong, big deflection in a fast fashion. So when major ventricular depolarization is going on, a very strong and fast vector approaching the positive electrode, needle suddenly move strongly, positively, but fastly. So needle suddenly move upward and comes down. So this wave this is called R wave, and this wave is due to major ventricular depolarization. This R wave is produced by the sudden upward deflection of needle, and this deflection is fast. It reaches rapidly to the peak and come down. And what is it is representing? It is representing the major ventricular depolarization, which is strong depolarization but fast depolarization, and depolarization is moving downward and leftward toward the positive electrode. So because depolarization is moving towards the positive electrode, deflection is positive. Because it is strong vector, so deflection is high amplitude, and because fast vector, so deflection is sudden up and down. Am I clear? After that, what is the next electrical event? Next electrical event is the last electrical event in spread of ventricular depolarization. So last electrical event is now current goes to the basal part of the ventricle. When depolarizing current reaches basal part of the ventricle, it produces small vectors which are moving upward and rightward. Now listen carefully. These basal ventricular depolarization produces small vectors which are moving upward and rightward. So these vectors are moving towards the positive electrode or away? Away. So when these vectors are generated, they are moving away from the positive electrode, they will produce a negative deflection. And because these are small vectors, so they will produce small negative deflection. And fast vector, so there will be small negative but fast deflection. So needle will move a little down and then back. So that will produce small negative deflection. Is that right? And this is S wave. So S wave is representative of basal ventricular depolarization. Now let's look at whole this complex. There are three waves. QRS. Three waves together are called QRS complex. Again listen. Q wave represent here in this study which we are doing. Q wave is representing ventricular septal depolarization. R wave shows that depolarization is spreading over major ventricular part, and S wave is showing that depolarization spread into basal ventricular part. Am I clear up to this? Now I will make one more diagram to make your concept more clear, and let's suppose we take the paper roll up to this point. Okay, then this frame also needs to be extended. Okay, our ECG machine has a now larger paper to see the other events also. Listen, let me make it very simple here. That okay,